Welcome back to the AI Ascent podcast. In this episode, we're talking with Zijian Zhang, who is the author of multiple AI research papers discussing human-machine rationale alignment. First, we'll go into some background questions, and then I'll let Zijian give a talk about his research papers. So with some of the questions, first, what university degree do you have or are you currently pursuing?
I currently have a Master of Science in Territorial Computer Science. Interesting because I'm studying in Germany and it is called Informatik in German. And it's currently in the Leibniz University of Hanover. And currently I'm on my way to pursuing my PhD degree at the same university and at the end of finishing the PhD defense.
And were these papers a part of your research at university or were they for your work?
Those papers are part of my research and were mainly contributing to my PhD final thesis. Some of the PhD students in Germany, like me, signed working contracts. However, the source of funds contracted varies. I'm kind of lucky because the sign of the contract is aligned with the topic of research of mine. So they're all for my research, topic of research.
And how much computational power did you have access to when doing this research?
I would say not so much because I was mainly focusing on the interpretability of my ML models, including training, interpreting by design models, conducting the post hoc interpretability, and so on. The model training was not only the bottleneck of our experiments. I was mainly on 1A100, sometimes with DDP over 2 or 4 V100, I would say. Those are in the clusters of the university, showing some respect to the colleague whose jobs are highly model training intensive.
Did you present these papers at a conference?
Yeah, sure. All those papers that I will briefly introduce sometime later will have been published in the conferences, workshops, including Wisdom, CIKM, CIR, CSCW, and so on. Also at MEI last year. So one of the benefits of working in the institute is to publishing in the institute, publishing in the conference, and being exposed and making new friends and gather some really valuable feedback from the researchers all over the world.
And how did you get into this type of work?
It was 2017 and 18, the beginning of the uprising, the over-parameter models. All the models performed so well, although we do not know how the models are designed. Although we know exactly how the models were designed, we do not know how the tensors are flowing all around the model. Therefore comes the interpretability of the deep learning models. So one direction is introspective, where we take a closer look at how these parameters are doing computation. Another one is model agnostic. We treat the model as a black box per se, and doing some calculating some importance scores out of it. And my master thesis supervisor, Professor Abhishek Anand, in the University of Leibniz University, and he suggested because he has such kind of a project that is hiring some of the PhD students, and the end of the story is that I become one of his PhD students, mainly focusing on this model agnostic interpretability.
Interesting.
Yeah.
And what's next for you after your studies?
Like we just mentioned a minute ago, I'm currently working on at the last step of my PhD defense, and I'm also currently an ML engineer in the company. I choose to join the industry instead of staying in the institute because I would like to see how the modern industry functions around the machine learning models. During my PhD study, I learned how to formulate ideas, making hypotheses, making experiments, analyzing data, writing papers, and of course, how to survive being rejected from the conferences, analyzing the data and writing papers, and all of those are really valuable techniques. But I have no idea about how this prototype, after the prototype is born, how to land it as an industrial product. Therefore, for example, the development, formulation, optimization, and automation of the product, as well as marketing and stuff, are really fascinating area that I have never met before. Therefore, after finishing my PhD in the university, I would like to work, drill, and grant in the industry for some years and learn all such products centralized in the topic as practice.
Perfect. Yep. Very interesting. All right. For this next part, I'll leave the floor to you to give a talk about your research papers.
Yep. Sure. So my research topic centers on the topic of the interpretability of machine learning models and human-machine rational alignment. So first thing first, as a background of the research, why do we need the interpretability for the machine learning? Since the first publication at AlexNet in 2012, if I didn't get it wrong, the development of deep neural models has been exploding, accompanied by their superhuman performance. The increment of their scales and the number of parameters makes it quickly beyond humans' ability of interpreting the objects and the prediction, the phenomena, like how the state models doing its prediction. Therefore, all those models are considered high performance in black boxes. For the information for our audience, the GPT-2 in 2019 already has 1.5 billion parameters. And the most recent, maybe not most, but quite recent GPT-4o has a number of parameters that large as even 200 billion. So it is important to find an approach to integrate the models and find out why the models are so well performing. This is not only to figure out the mechanism behind the models, but also important to do the model recursing and training better performing model with fewer biases that is more human aligned and human friendly. Therefore, there has been a lot of creative and insightful approaches focusing on how to do the interpretation. We can roughly categorize them into post hoc approaches, approaches grounding to task, and interpretable by design models. I won't go into much details about all of those three categories, but it is actually worth mentioning that all those categories are not mutually exclusive and there are huge overlap in research. We mainly use the attributes-based post hoc approaches and rational-based interpretable by design models in my PhD research. And don't get afraid of all of those jargons. I will definitely do some explanation afterwards. Our research is mainly around the rationals extracted by those interpretability approaches, either attributing scores to the input features or selecting subgroup of the features as the evidence or the rationales. We also gather human rationals from humans and try to align the rationals from both machines and humans. So that's where the title of my thesis, aligning the human machines rationales, comes from. So therefore, my research is mainly centralized around all three research questions. Those are first, how do we quantitatively measure the distance between the human and machines reasoning? And second, given the dissonance between the human and machines reasoning, can we train the machines to rationalize following the human's observation? And third, given such dissonance, can we translate the machine's reasoning from the other way around into the form that is better understandable by humans? So let's then start from the first topic, measuring the distance between the human and machine's rationales. This research actually focuses on the image classification, but it can be easily transferred into different topics like the sentence classification, the tabular data classification, and so on and so forth. In this image classification data specifically, we crop the underlying image into patches, call them superpixels, and consider them as features of the input. Why do we actually do that? Why do we convert all these superpixels as the inputs or features of the input? This is actually based on the corresponding research on the topic of human recognition, where the human beings recognizing the items of image do not when we doing the recognition, we do not copy each every pixels of the image. We only take it by part. So if you are heard about the concept of Gestalt psychology, you might have seen such kind of image where most of the mostly a triangle, but some edges of the triangle was covered and unrecognizable. And all of us, but however, could recognize all of those. This is a triangle if we only see all of three angles. Given that's the reason of the cognition is selection of part of the image, the preference of selecting whether components should be visible becomes tricky. Seeing all three angles is much more helpful than only seeing one angle and two adjacent edges. So this selection of preference of features when recognizing the item by part is therefore defined, in our case, the reasoning of both machines and humans. So for gathering the machine's rationales, it's easy that we can simply apply some post hoc interpretability approaches like SHAP, SHAP, if you're not familiar with that framework, to do the underlying, to help the underlying model to calculate their attribute score for each of the superpixel. Then we can rank the superpixels according to the feature attributes. As for human reasoning, it's a little bit trickier one that we conduct a cross-sourcing job to ask multiple participants online to sort the superpixels. We present this split image and ask the crowd workers to click on this superpixels one after another according to their preference of the importance that is helpful to recognize the item in the image. After that, for each image, we aggregate the human sorting the features all together and calculating their distance ranking from data from the machines. And that could be that actually produces the type 1 dissonance between the human and machine reasoning. So then we have we are curious about why which team actually either humans or machines are a better selector of feature ranking under our circumstances. So consider that the preference of the features are used to help the humans to accomplish the cognition job. We hired actually another group of crowd workers called the guesser group, uncovering the superpixels accumulatedly piece after piece. And the order of the revealing is following the rank of the either produced by the humans or the machines. And we ask the second group whether they can make a guess what is actually in this image as soon as possible. Then this difference of speed of making the good guess is actually called by us the type 2 dissonance between the human and machine's rational difference. So the first task was to find out which is the most human-like feature selector. We can rank the all models, underlying models, from most human-like to least human-like. And the second experiment even put the machines and the humans behind the same starting line. It compares who is the best feature selector to result in faster guesses. So it is really fascinating that in the second experiment, one of the machine learning model, if I don't get it wrong, is ResNet, results in better feature ranking than human selectors, resulting in even faster guesses. We inspected the feature rankings and found some explanation for that. Some machine learning models learn to cheat or all of it to the features that are actually relevant to the image label, but they are much easier to recognize. But sometimes they are really wrong really wrong reasons. For example, in our paper, we published an example. The image label is kimono, a traditional Japanese clothing. The human rankers tend to rank the clothes per se as the most important features, which is really hard to recognize when uncovering patch after patch. But the machine learning models select the face of the human wearing this kimono. Those are faces of Asian ladies those are covered by traditional Japanese white cosmetic, which are highly iconic. This actually indicates a possible bias of the models. What if the kimono is on a hanger instead of being worn by human beings? Would the model predict well as it does now? So this kind of question actually urges us to continue the nexus research, developing AI system that can explain their decisions and even mimic human explanations. We created, therefore, a model called XPRED, short for explain and predict, then predict again. It doesn't just make predictions; it shows you exactly what it why it makes such predictions by showing the evidences. So we would think of the XPRED as a detective. At first gather the evidences, what we call the rationales as a subset of the input features, and then uses the evidence to conclude. The humans can supervise both steps, making sure the evidence makes sense and the conclusions are logical. So while this select and predict approach is not entirely new, our implementation addresses some crucial challenges that the previous methods struggled with. Earlier approaches can fall into camps. Some researchers use that we call the pipeline models, where one system selects the evidence and another make the prediction based on the evidence, kind of like having a detective gather the evidence and then passing it to the judge to make a decision. Others use the end-to-end models, where everything happens in one integrated system, and the evidence is generated as output of an intermediate layer. So both approaches had their problems. Pipeline models sometimes collect evidence that wasn't useful for the final decisions, while the end-to-end models can really find a sneaky shortcuts that look good on paper, but do not really understand the semantic input. I remember there's an example where the model learns to highlight the first token in the input whenever there's the label is, for example, positive, and select the second token whenever the final prediction is negative. This is really interesting, but really harmful trick and way of doing our fitting. So our key of the XPRED is to adding what we call the multitask learning to the evidence selector, the first phase, or the detective, whatever we call. Imagine it like training a detective in the first phase who do not only collect the evidence, but also makes preliminary judges about the case. By doing both tasks simultaneously, the system learns to collect the evidence that is relevant to the final decision. We use BERT, a powerful language model back from that time, and as the encoder of both phases, and train our pipeline model with multitask learning equipped in the first phase to identify the rational text and make initial predictions, and then the second phase make their prediction based on the evidence only. So we tested XPRED on various tasks like fact checking or reading comprehension and it's a sentiment analysis task. It is not only making accurate prediction, but also identify the relevant evidence. As much as as far as remember, it shows 40% of the improvement of how well the system could identify the right piece of evidence. So this breakthrough of the development of the model XPRED actually leads us to develop two practical applications using this interpretable by design model XPRED. So first, we built the application called FactSplain-AC, which is short form of a fact-checking tool that does not tell you whether there's a statement you input is true or false. It shows you exactly why. For instance, if someone claims that well, Microsoft is a Chinese company. The system then searches, for example, from Wikipedia, find the relevant information, they then highlight the specific evidence that prove the evidence or disprove the claim. So user can then provide some feedback if they think that system got something wrong, helping the models learn and improve over time. Another application is called Spark Assist, which actually helps to evaluate how the robust AI models are by tagging them, whether which we call which we call the counterfactuals, where the most of the input features are kept the same, while only a part of the input features are altered. For example, if a sentimental analysis model correctly identifies "I love this movie" as a positive, how does it handle "I love this film"? It changes if we change movie to film, and then it suddenly results in the movie. It results in the model's prediction flips. Then there's it is actually a alarming sign suggesting the model might be using some superficial patterns rather than understanding the meaning to do the prediction. So this second application allows us to allows the end users to interactively construct new counterfactuals to test the decision boundaries of the models by alternating the rational words formed by the express. This generations of the counterfactual continues until the model's prediction flips. It indicates that we have just crossed the decision boundary of the model. Then the counterfactuals living near the both sides of the boundary are highly valuable because they outline the local structure of the decision boundary. Both of those, so those counterfactuals, if they do not make some result in the predictions like we expected before, we can use it to train a more robust model afterwards. So both those applications actually showcases how making the AI system more transparent isn't just about understanding themselves better. It's also about building tools that can work alongside humans, learning from the end user's feedback and becoming more reliable over time. So after introducing all the things around the express, the second approach is, then let's go into the third approach. This is the most recent published from us is the DISCO. So given the express resolve the dissonance from one direction, they're training the machines to mimic what the human suggested to. And DISCO actually converted that's the other way around. Resolved it by actually translating the machine rationales into a form that is understandable for humans. And this form, spoiler alert, are a bunch of rules. We mentioned a minute ago that sometimes the AI can make decisions based on the superficial pattern label relations rather than actually understanding the content. Our DISCO model can actually discover such kind of overfitting and cover it in a bunch of rules. That's where the title of this paper, Discovering Overfitting as the Cultural Rules for Text Classification Models, in short, DISCO, comes from. So to start with introducing the DISCO approach, let's just start from one picture where you imagine you have an AI agent that supports provides the predictions on the movie reviews, provides some predictions over the semantics over the movie review and book review. Now, if the AI system was trained on one dataset where perhaps purely by coincidence, every review containing the phrase "this book" was positive, and every review with "this movie" was negative, it might start making prediction based on those phrases alone, completely ignoring the actual content of the reviews. Even if you figure it, you give it something like "I hate this book so much," it will probably just give you the passive prediction. So it's just judging a book by its cover, literally. And previous approach could catch this kind of shortcuts but with some limitations. Some methods could only take a look at one example at a time, while others require too much human interventions or they were just too slow to be practical. That's where this code steps in. We developed it to automatically detect whether the AI models are taking this kind of shortcuts, and it does that is across the entire data sets, not just individual cases. Therefore, it produces so-called global explanations for the model. We at first feed the models with all of the training set instances in the training set and let it make predictions. Then we mine the co-occurring input patterns, for example, the book previously, and their corresponding labels, for example, the positive. Then what makes the disco special is how it borrows data from the cultural inference, the science of figuring out what actually causes what. Instead of just finding out the patterns that happen to occur each other because of maybe statistical correlations, we can determine whether the model is actually using these patterns to make decisions. We do this by creating some counterfactuals, again, the counterfactuals, varying the input where we keep the suspected shortcuts, but changing everything else around it. Then here is a cool part. We tested whether the model's decisions, but whether the model's decision changes when we put all of these counterfactuals. If the model's predicts remains the same under the same patterns, regardless of the context, that's a huge alignment sign. It means it's probably using the shortcuts instead of understanding the full content of the sentence. In our experiments, we test this code in three different ways. First, we check if our finding of the rules match whether matches with other localized rational-based models. They did. The overall 65 out of 100% of agreement. Then we deliberately introduce some of the biases into the training data to see if this score could catch them. It did, especially in the case where the biases were strong. And finally, we look at whether the disco could identify whether the models are making the right prediction, but for the wrong reasons, thinking of it like getting the right answers or on a math text, but using totally wrong methods. It also does according to the votes of according to the votes of all of the researchers behind the paper. So that what particularly exciting is that this approach could be really valuable for improving AI systems and models, especially as they become more complex and widely used. And by the way, we are already thinking about ways to extend this work on the large language model, and maybe using more complex patterns as the source of the causing the biases. So that's all for what I've done for my PhD research. Thank you for your patience.
Awesome. Very interesting. Yeah, thank you so much for that presentation. It was really great having you on the podcast.
Thank you.